As an example of something that isn't a vector space, all polynomials of degree n for some fixed n. This isn't a vector space for a number of reasons. Perhaps the quickest is to observe that there's no zero polynomial in here. 0 does not have degree n. But we could throw 0 in here by special fiat, so that's not a very important problem. A more significant problem is that this vector space is not closed under addition. You can have a polynomial of degree n plus a polynomial of degree n and wind up with something that is not a polynomial of degree n. What is a vector space is P sub n, the set of all polynomials of degree less than or equal to n. So just a minor technical issue is whether the set as described includes 0. Some authors say that the constant function 0 doesn't have a degree. Other people say it has a degree of negative infinity. And if you're willing to accept that negative infinity is less than n, the 0 polynomial was included in here. Otherwise, you have to make a special point of including it. This is a vector space. It's a subset of the continuous functions. It's also a subset of the functions and a subset of the differentiable functions. Well, what's important is that it's a subset of a vector space. Closure. Under addition. Check. Adding two polynomials can reduce the degree if things happen to cancel, but it certainly can't increase the degree. You can't add a fifth-degree polynomial with another fifth-degree polynomial and suddenly have a seventh-degree polynomial. Closure under scalar multiplication? Check. Multiplying by the scalar 0 gives you 0, and we've made sure that 0 was in here. Multiplying by any other scalar doesn't change the degree. 0 has to be in there. Check. Either because negative infinity is less than n, or because we specifically threw it in there. We'll come back to this example rather often over the next few weeks.